Okay, great. So let's just forget about that one right now. So modeling local warming using remote sensing data. Just to give you a quick, introduction from my part. I was a student in URPD in Kulna University from 1994 up to 1998, and I completed a master's in Sweden back in 2001, and completed my PhD from the University of Tokyo in 2006. And I became an assistant professor in 2006 when I joined at URPD again after completing my PhD. And in 2007, I actually left the country again. And I went there several times, but I did not have a chance to meet many of you. But I believe we'll be having a kind of very strong network from now and onward, and we'll be meeting frequently at some point, using Zoom or other things. So be taking around hopefully 30 minutes, and I will be seeking your attention. And before going into the detail of the presentation, I'm again thanking the URPD KU and the people who are actually listening to me right now, and who are trying to adjust their volume, adjust their technical issues and the glitches that we are coming across. And for your patience, I'm really appreciating that one. So the three major kind of things I'll be talking today, it's about the background, about the research program that we had, and especially I actually led this research program. And second, the technical part of this research program, and third, I'll be taking a few questions from you. And I'm telling you again, it's almost 1:15 here in the morning. So you can easily imagine I should be sleeping by this time, but I'm really excited to talk to all about my research. So just to start with few basic things, it's about the environmental studies and remote sensing. As I am actually working in the Department of Environmental Studies and Geography at St. Mary University in Halifax, one of the major, dimensions of my research is to contribute technical support to the Environmental Studies Department. So the technical things we do mostly using remote sensing data and a GIS dataset. So the first thing I actually contribute, it's about land use change and land cover change. If you know about it, probably it's called LULC, assessment. The second one, forest fire assessment, it's a natural disasters in Canada. So, we are highly vulnerable in some places, mostly in Alberta, British Columbia, if you know the country well a little bit. It's in the kind of west coast. They are very much vulnerable with forest fire. So we actually received a project to, delineate the forest fire vulnerable areas, and how could we assess the fire hazard, how could we actually minimize the situation by engaging people to make some clear cut the forested areas, and save the communities.
Raman sir, could you please share your screen?
Yeah, I'm actually sharing, probably, isn't it?
No.
Okay, so again I'll have to share. So many things is going on all together. Okay, I thought maybe I was just sharing. Anyway, so if you just take a look in these pictures on the left-hand side, it's in Bihar area in India. It's just north of the country. We actually tried to delineate few areas of land use and land classification, land use change classification. And the second one, it's about the forest fire assessment we actually completed in the north of Alberta, the province of Alberta. The other picture you can see, it's in Sylhet area. In whenever there was a kind of big flood, we actually tried to understand how the flood actually engulfed the water, and it was a kind of bowl type of area. And because of the rainfall, because of so many different things, there were a lot of dynamics. So we wanted to see why did it happen, and how did it how did it can be assessed. So that was kind of one of the goals of this research. The third one, the fourth one, the right-hand side picture, you can see it's a soil classification in agricultural map preparation in agroclimate crop suitability analysis in one of the areas in Mymensingh in Bangladesh. So we actually conducted that research as well in there. But what I'm going to talk today, it's about, the application of remote sensing to model climate. So you probably all know about the climate is a kind of major, threats these days for us, because climate should not be a threat, but now it's a threat because it's changing, and it's changing very rapidly. Because of that, several organizations are working, and the IPCC also won the Nobel Peace Prize even for because of this climatic change and research contribution. So most of the scientific research and the domains are highly working on the kind of global level, the regional scale, or at country scale. But being a planner, and I was kind of like having a question by myself. When I attended one of the seminars in Florida back in 2000, probably 11, I actually found not so many research actually have been conducted to understand the local, changes of the climate. So I thought like that could be possibility. I can, I could actually contribute something. Because of that, I actually went back to school again, to do my second PhD. And it was from the geomatics engineering department at University of Calgary. So I conducted this research in there. And I actually was thrilled to see like if I could actually generate some maps that could demonstrate, a local scale, a city scale, or even in a community scale, that might actually help a lot of people to make future adaptation plans and to prepare some guidelines for climate. So what I did, like mostly the spatial and temporal dimension we know we have in remote sensing data and satellite imageries, you probably know even sometime better than me because you are kind of studying remote sensing in fourth year. So who just completed the remote sensing course, they know about the global scale, regional scale, and local scale. It's called the spatial scale, and the temporal scale means like the daily data, weekly data, and monthly data. So my prime objective was to prepare something, that would be freely available. So the data set, remote sensing data is very expensive, and especially whenever you are coming to, the Western world, a single, image would be costing you around like $15,000 to $20,000 if you actually wanted to get 1 centimeter to 3 centimeter resolution image. Or like even if you wanna get like 1 meter resolution image, it would be very expensive too. Because of that, my intention was to generate something based on freely available data, and it should not be costing people. It should not be costing any extra burden for the government, so that it could be helping the decision makers with free of charge and free of cost. That would be helping people. So I then I explored like Landsat 5, Landsat 8 data was available. Modi's actually launched in 2000, in February, in the month of February, and Sentinel data was kind of freely available. So Landsat 7 data was freely available, but it was not useful because there were some strips. So there are some kind of issues with the satellite. So all of the data is kind of error based. So you cannot use that much for scientific, research that much if you don't correct that one. And Landsat 8 OLI, it actually launched in 2013. So, it was a little bit late. So because of, the freely available data as the Modi's data was in hand from 2000, so I heavily relied on Modi's data in the first place. Then you see, Canada is a very big country. So my plan was to, produce something for the whole country. Then I invented and I explored, not invented, it could be a wrong word. I explored that, even if I take a province, like province of Alberta is this one, it's almost like 5 times bigger than Bangladesh, you see. So it would be even, a huge cost for me to, not like the money, it's kind of like the time cost, to analyze that huge sort of data set. But still I took the challenge to, start with the provincial level so that I could, bring it forward to the country level. And, the Canadian land area is the second largest country in the world. And it's almost like, 10 million kind of square kilometer area. It's a huge country. So it's somehow not that much possible to, do something in like a 3 to 4 years time window to consider the whole country. Because of that, as I was just living in Calgary, so I picked the whole province in here. And this map, you can easily see there is a little problem, right? For example, the climate station-based data, people actually prepared these regional maps. It shows like similar kind of, area, like Calgary, Regina, and Winnipeg. These are 3 different provinces and the capital of 3 provinces in here, like Edmonton is the province of Alberta. all these provinces, like they are kind of demonstrating similar climate, which is not correct. Okay, so it means if you go to Calgary right now, probably the temperature will be -17. If you go to Regina right now, the temperature would be around -40. If you go to Winnipeg right now, the temperature would be like -15. So it's not kind of same. So I actually questioned this method. So when I questioned this method in literature, I found most of the data set they collected to prepare this type of map was based on a station. Okay, so whenever you have the station-based data, momentarily it's highly depending on very specific site. But the satellite, it is capturing the like the pictures in everywhere. So why don't we depend on the satellite images, so that like I could get the data for everywhere when there is no kind of even the stations, still we could capture some data. So by keeping that in my mind, I actually started to dig into detail. So when I dig into detail, I found I should actually give it a title. So I titled it as local warming model. Okay, so it means it's representing the local area. And why studying local warming? It's because of like global scales are very big, and the resolutions are very coarse, and it doesn't represent the city areas. Even it doesn't represent small kind of provinces. Definitely, there are scientific challenges that I wanted to take, and also it would be aiding for future adaptation and land use planning. Now, the research program I actually divided in 4 different parts. The first part was to identify the gaps that I did eventually in like 3 to 4 months. After that, I actually picked up like a modeling of local warming using 1961 to 2010. That particular time period is a 50 years time period. And third, band sharpening is a kind of technical term, though I'm not going to explain that much, but just to like fuse the data, because if we have the 1 square kilometer resolution data that MODIS actually gives us, so we can actually bring it to 15 or like 30 meter based on some band sharpening with Landsat 8 data set. Okay, so this is a kind of technical term, and it's a kind of like fusing method. I used several different types of fusing methods. And the last one was to enhance the image into 15 meter. So that was the kind of major part. So to do that, I'm not going to explain that much about the knowledge gaps, but to just show you where the climatic stations are being placed. And if you have question, please write it down, because in the middle I cannot see you. It's not a kind of very much interactive presentation. If I used to give the lecture in a kind of big auditorium, it would be helpful, but I'm not looking all of you. I have only like 4 or 5 people in front of me, so please write it down, and I'll be taking the questions after the presentation. And there will be a moderator, probably Dr. Hassan Al-Kabir. He will be helping me to ask the questions. So you can see these are the kind of climate stations location. So they are mostly in the border area, because almost 85% of the Canadians, they are living within 200 kilometers of the US border. So it means like we don't want to go further north. So it is also very expensive to establish these climatic station in further north, even though for our military region and for other things we need to place some stations in there, but they're not that much big numbers, and it costs a lot, at least like 50 to 60,000 Canadian dollar it takes to establish a station. And to capture the data regular basis, it also costs a lot of money. And some of the stations we do have in here, you can only go by airplane or by helicopters. So we have the like a satellite on our hand, like the satellite imagery is on our hand. So we can actually try to understand like if they could give us the pinpoint resolution to demonstrate the model. For the case of Alberta, you see like the WMO, it's called World Meteorological Organization. They actually standardize some of the climatic stations. So these climatic stations are kind of sporadically distributed in the province of Alberta. And you can see like if this station is giving us is called Fort Chipon, this name of the place, it gives the data for whole area here. So if this station tells us like the temperature is 5 degrees right now, it means this whole area is representing 5 degrees. Think about it. It's not true actually, right? And here you can see the variation, because most of the cities are in here in this area. So they have a lot of climatic stations. And interestingly, Some climate stations are being placed only for 4 months during the summer periods. Why? Because at the time there are a lot of forest fires, like happening. So just to monitor those things, we actually place 4 months. There's, like sporadically, we are distributing several, climate stations in there. So my first task was to, like demonstrate the model of 1 kilometer spatial resolution. And I'm not gonna explain this, just to give you the schematic diagram that you may actually be able to understand. So I used the MODIS 8-day composite image. So for a particular year, there were like 46 images, okay? And I received the data for air temperature normal. So we call it 30 years average of climate data, that is the normal. So we have like 3 climate normal data in our hand in Canada. So one is from 1961 to 1990. The second one is from 1971 to 2000, and the last one is 1981 to 2010. So I used that data set from Environment Canada website, and Environment Canada, the Ministry of Environment, and the yearly average air temperature from 2000 to 2010. So 10 years time period. I used the data also from Environmental Canada. So you can see like 3 different types of data I used to generate this model. So you might actually ask, why did I need to use only these 3 types of data set? Why didn't I actually take the data from agricultural department or other departments? So interestingly, in Canada, this data set is free. But for the US, you need to buy this data. That is very interesting thing. So it's our taxpayers' money. The other point here, I'm not paying any tax to the US government, but this data is free, you see. So this is from the US taxpayers' money. So everything was free at this point, and we actually used all this data set and then generated the model. So interesting part is that when I actually started to generate the model, I had a lot of issues. The first issue was that there were some data, there were gaps. It means like the 46 images I collect for every year, some images were kind of having a lot of clouds. So how to, get out of this cloud? And there were some stations that did not have probably data for 1 month. So what I did, I generate an algorithm, like this way. So this is probably, just think about it hypothetically, this is a kind of, the lower one is the climate station data. And this one is the top one is the kind of satellite data. So when I find a gap, like this pixel of that particular day is kind of, error-based or like cloud-based, cloud contaminated, then what I did, I actually call the exact, dates, station data to fill that gap. And vice versa, whenever there is a gap in here, so I called the, data set from there to fill this gap. So that was the kind of algorithm I used. And you might actually ask me, so if there are gaps for 2 cases, so what would happen? Then what I did, I actually went to Ministry of Natural Resources dataset and then tried to collect that data for a specific day and fill the gap in that way. So it would actually fill both of the, days for satellite data and for the station-based data. So it was a kind of easy algorithm, but whenever you actually do this one, it's very, exhaustive, you can say. Like it's a pretty much laborious thing to do. And then I'm not going to explain these things. Let's just get to the final production. So once we actually generated the map, and you can see it's a beautiful map of the province. It looks really great. And it shows temperature changes from like 1961 until 2010 in many places more than 1 degree centigrade temperature. And you might notice like it's a cold country, 1 degree centigrade temperature increase would be really great. But it's not, because it has a lot of issues with the biodiversity, the forest, and the lakes we have, okay? So you can easily imagine like many areas it's red, some areas there is no change, like the green areas, and some blue color areas it actually changed into negative direction. So the negative direction, it happens because of some forestation. We did some extensive, forested, programs in there, and also some, cooler vortex that actually came from the northern part. So probably from, Yukon territory, from other territories, from Alaska, those vortex actually came. And because of that, it was like a little bit cooling. But that percentage is only like 2.91%. So you can say like it might be also error and you could neglect. But the worrisome issue is that we have 2 critical, national parks. So if you know about national parks in Bangladesh, we do have few, probably like Sundarbans is one of the assets. In Canada, we do have like few national parks, and 2 of them are kind of very prominent. It's called like Banff and Jasper. If you just Google anytime like Banff and Jasper, you will see like the beautiful lakes, like the beautiful mountains. It's the Rocky Mountain area. So these are here. So they actually found, like our study, we found like, this area is kind of changing the temperature the most. So it means the lakes could be, like depleted, like the Rocky Mountain could be having some issues and the biodiversity might be losing. So still we could not pinpoint, like Calgary, I was just sitting in here. So it shows like whole Calgary area, like the temperature changes around like 1 degree centigrade or more. So this is the kind of urban area. And you can see Edmonton is the capital, and it did not actually change that much because, like it's kind of decaying. The city of Edmonton, not so many people are coming these days in Edmonton because it used to be like 1.2 million people earlier on. But the, like urbanization rate is going a little bit down in there because of job market, because of other, like opportunities in different places. But Calgary is still, like accepting a lot of new people. So it means like the urbanization rate is really, really going very high in the southern part, especially in Lethbridge, Medicine Hat, and Calgary area. So what I found, it's a kind of 1 square kilometer resolution map. So I was not very happy with that only. Like 1 square kilometer, it represents like, like a very big area. For example, if you consider the campus in KU campus, it will not be more than like, 5 square kilometer. So it means like only 1 pixel will be represent a whole campus. So I was just interested to see like if, like at kind of yard level, kind of like in a kind of house with the yard, with the backyard, with the front yard, how much temperature actually changed. Because of that, I thought like there are alternative options. So Landsat OLI, 8 OLI, they had kind of 15-meter resolution. So if I could actually transform this map to 15-meter, then it would give us, like give me a very critical clue to see if the temperature actually changes inside the local area. So then I can say it's a local warming. To do that, I did the second thing, you can say like enhancing the spatial resolution. So I wanted to enhance the resolution, and I did it through pan sharpening. So I'm not going to explain that, like method right now. If you are interested, I can send you the paper. You can just take a look. So I actually generated the model in this way, like the Landsat, like a multispectral band. And the panchromatic band has like only 15-meter resolution. So I actually use this data set to get the NDVI, NDWI, NDVI. These all are kind of technical things. You know about it for sure, but I actually, like I'm not going to explain that much. So I enhanced the resolution from multispectral band with 30-meter to 15-meter. After finding this relationship, there are like, like millions of data in here. You can see like these gray areas. It's only 0.17% this gray area. These are kind of, I am considering as error. See, so it means like there are millions of data set in here, and I tried to mimic them, tried to see like what are the kind of R-square values in between those variables, and I found in most cases like it's approximately 80 to 90%. So whenever I found that relationship with the pan and the blue and green band, then I actually tried to like adopt the star FM method to like fuse the data set to enhance it to 15-meter. And when I did that one, then I actually again brought the kind of MODIS data set, the NDVI from MODIS, the EVI from MODIS, and the NDVI and MODIS from like the pan sharpened band. Then I tried to mimic them and found a very strong correlationship. And I actually picked up Calgary area. And you can see now inside Calgary area, there are some differences in different areas, like the temperature did not change as you saw in 1 square kilometer, like map. So this is kind of one of the kind of, best models so far, like to represent local warming. So I actually ended up in there and I completed my study in there. And after that, I thought like I would be going even further to enhance this one to 5-meter. Okay, so it's like 25 square meter area, but that would be kind of the next thing. So what does it say actually? What these maps actually say? Because for the social scientists, for the scientists, for the physical and, like human geographers, everybody, they want to, like explain things properly, right? So we have these things in our hand. Now, what could be the conclusion, or what could be the concluding remarks from us? So what we found, the local warming trends were observed 88% of the province. So think about it, the province is like 5 times bigger than Bangladesh. And 88% of the province has been experiencing, like the climatic change more than, like maybe 0.25 degrees centigrade up to like 2 degrees centigrade temperature. And the generic spatial patterns were summarized as like up to 68% of the areas experienced local warming trends up to like 0.25 degrees centigrade to, like 0.75 at some places. And 5% areas underwent higher than 1 degree. So that 5% we, like identifies as critical area. So the government, like could take the benefit to see from this map, like which are those areas. And lower percentage, like around 2.91 percentage, are kind of going down temperature. So those are not having kind of positive, like change. The other thing, if I tell you, still people are coming, so I'm just giving them the admission. So the other thing is spatial extent of local warming during the period. I actually generated this model from 1961 to 2010. So the next climate normal data set will be available in next year. And I hope like I will be, preparing the next model. And especially as I'm living right now in Halifax, it will be about Halifax. And the contribution of the science, if you say like how did, like I contribute into the science. So the first thing would be like the 15-meter resolution is not, in business right now. So it was one of the prominent, contributions. And because of that, we actually received, like a $200,000 project, like to find out different types of, climatic impacts in the province of Alberta. That project is going on right now. And several government organizations are asking us for the training, like how could they actually use this freely available data? And probably Erdashimoji is not a free software. So we had to, buy kind of like 5 licenses for 5 municipalities. And we actually started to, help them to build the capacity for them so that they could actually pinpoint their issues. The scientific methods, if you are interested, you can just easily Google and you can find all those, scientific evidences in there. And I am pretty much thankful to several organizations who actually supported for this research in the last 5 years. Especially it's called NSARC, you've heard about the name. It's called Natural Science and Engineering Research Council of Canada. And Alberta Innovates, that's the kind of prime, innovative scientific organization in the province of Alberta. And Cenovus, I'm pretty much grateful to them. They are kind of oil giant, and they actually gave us $200,000 to, investigate more. And the National Fire Information Dataset, they're also giving us some money to investigate their one in province of BC, like British Columbia, University of Alberta, and Schulich School of Engineering and the University of Calgary, and definitely the Geometry Grad Group. Main references I used for today's presentation are like these 4. And if you actually want to Google for some media attention, you might notice a few of my interviews would be in television. So they are probably in YouTube. And 75 different outlets of newspaper in Canada and in the US, they actually, made it kind of a big news. And a couple of them are in here, like CBC is Canadian Broadcasting Center, and the Global News is the Canadian Prime, newspaper. So they actually published that one. Future research plan. I have, a very few things in mind, but, what I'm trying to build a community-based climate adaptation planning research cell in Canada so that we can actually have some scientific, evidence. Based on that, we can actually make some adaptation plan. And also natural disaster and land use planning. How could we actually utilize the scientific evidence to make a kind of future disaster, risk vulnerability assessment or vulnerability planning? Those are the kind of, major things I have in my mind. And I hope it did not go beyond 30 minutes as I actually promised. So if you have any question, please feel free to, ask. And thank you very much for listening. And I'm really appreciating because you did not, ask any question inside. Thank you.
Okay, now